In the last lecture, we have learned that if there is nothing resisting charge movement, for example in vacuum, charges would keep accelerating under voltage difference. We also learned that there are two main types of materials called insulators and conductors, depending on whether or not current can flow through them. Conductors, for example metals, let current flow through them. But how do charges move through those conductors? Do they accelerate like in the case of vacuum? Or does something else happen? Let's recall how charges, that is, electrons, move through conductors. Electrons jump from one atom to the next. So they are bound to stop at every atom on its journey, even if that's for a fraction of a second. It's as if the atoms inside the conductor are trying to stop or resist the electrons from flowing. So, unlike the case of vacuum, electrons in conductors can't just keep speeding up. Electrons do start off with huge acceleration and gain speed as they leave their parent atom. But shortly after that, they have to turn that speed down to land on the next atom. As a result, after a while, they can't get any speed boost, and the electrons reach an average speed and don't speed up anymore. So, all in all, it turns out that in conductors, electrons hit a constant average speed, unlike the case of vacuum, because the conductor atom resists the movement of electrons. And if electrons are moving at a constant speed, the current would also be constant, because on average, every electron would take the same time to flow from one point to another. By the way, all of this happens in a fraction of a millisecond. It takes almost no time for the electrons to reach their top speed. Well, electricity is fast after all, and that's why we use it in the first place. So, from outside the conductor, the whole scenario would look something like this. If we apply a voltage difference across a conductor, we would observe a constant current from high voltage end to the low voltage end. The exact amount of current would depend on a few things. For example, if the voltage difference were higher, the electrons would achieve a higher average speed than before, and the current would go up. So increasing the voltage means the current also increases. In fact, in conductors, current increases proportionally to the applied voltage. That means if we double the voltage difference, the current would double as well. And if we halved the voltage difference, the current would also be halved. This fact is mathematically represented like this: I proportional to delta V. This is just a sign we use to mean if the right side is doubled, left side would also double. An easier way to write the same thing would be to write I equals G delta V, where G is some constant. Say G is 0.3 units and you apply a voltage difference of 10 volts across the conductor. You'd get a current of 3 ampere. By the way, note that delta V here stands for voltage difference, not the actual voltage. It doesn't matter what the actual value of the voltage is, as long as the difference is 10 volts. Now, if you double the voltage, that is, you apply 20 volt voltage difference, you would get 6 amperes of current. Like I said, doubling the voltage difference means the current would double as well. If you can recall from high school physics, this is actually one of the basic laws of electricity called Ohm's law. Ohm's law simply states that current through a conductor between 2 points is directly proportional to the voltage difference across the 2 points. If we write Ohm's law in equation format, we need a constant. We just arbitrarily chose the letter G for this constant. As you can see from this equation, the value of current not only depends on the voltage, it also depends on the constant G. This constant G is called conductance because it signifies how good of a conductor it is. For example, if you took a conductor that has a conductance of say 30 units as opposed to another conductor that has a conductance of 0.3 units, for the same voltage difference, it would conduct 100 times more current. Higher value of G always means better conductance. That's why G is called conductance. For example, a piece of copper wire will have a much higher conductance than iron, and iron would have a much better conductance than a piece of wood. In fact, insulators like wood doesn't conduct at all. So, conductance of an insulator like wood is almost zero. And you can see that if conductance is zero, even if we apply a voltage difference, zero conductance means the current will be zero, which was the defining behavior of insulators. On the other hand, theoretically, the best conductor would have infinite conductance. Of course, we cannot have infinite conductance in real life, but 1 feet of household copper wire has a conductance of about 20,000 units and sometimes even more. So that's pretty good as well. Different conductors have different conductance. This is because some conductors attract their electrons more than the others and don't let go of their electrons that easily. And as a result, they slow down their electrons or resist their electrons' movements a lot more, causing a lower current. For this example, since conductor B conducts less current than A, B has a lower conductance than A. So it turns out the secret of being a good conductor is to not resist your electrons' movement. Lower the resistance, higher the conductance, and vice versa. In fact, the resistance of a conductor is defined by the inverse of conductance. It should be intuitive enough because they are basically the opposite of each other. For example, we saw that insulators have almost zero conductance, or synonymously, insulators have a very, very high resistance, ideally infinite. And the best ideal conductor will have zero resistance. So, resistance and conductance is just the same information portrayed in two different ways. And for the same reason, conductors are also called resistors. Basically, we can use resistance instead of conductance anywhere we want. For example, this equation is just another mathematical form of the same Ohm's law. In fact, the term resistance is actually more popular than conductance. And since they portray the same information instead of conductance, everyone uses resistance. If we slightly manipulate this equation, we can actually use Ohm's law to define resistance. And from this definition, it's clear that the SI unit for measuring resistance should be volts per ampere. We use resistance so much so that we gave this unit a name, Ohm, which was named after the physicist who first discovered this law. For example, saying this conductor has a resistance of 1 ohm is the same thing as 1 volt per 1 ampere. Exactly the same thing. And what it physically means is that if you apply a voltage difference of 1 volt across this conductor, you would get a 1 ampere current. By the way, that symbol is a Greek letter and we use it as a shorthand for Ohm. Back to the point. We know that in conductors, if you double the voltage difference, the current would double as well. Does that mean if we doubled the voltage, would the resistance change as well? Well, the answer is no. because resistance is the property of the conductor itself. If you don't change anything about the conductor, it will have the same resistance as before. And you can see that from the definition of resistance, instead of saying 1 volt per 1 ampere, you could also have said 2 volts per 2 ampere. They are the same thing because 2 divided by 2 is just 1. And we get 1 ohm just like before. So then what does 2 ohm mean? Well, 2 ohm is the same as 2 volt per 1 ampere. So it should mean if you applied 2 volts across this conductor, you would get 1 amperes of current. Compared to the 1 ohm resistance from before, this time we only got half of what we got earlier for the same voltage difference of 2 volts. And that should be correct because higher resistance means lower current. Before I end this lecture, I would like to address a missing puzzle piece. If you think logically, you'll find that the total energy isn't constant when electrons are flowing through the conductor. Try to figure out yourself what's happening before I reveal the answer in the next lecture.